Okay, let's start. So last time Felix talked about the lower bounds and all these proofs about contrastive learning, and in the exercise basically you had to implement the contrastive learning objective. But now we'll take a closer look to actually what's happening during this pretext task in contrastive learning, at least for the beginning. So for two views and a batch of n images, can you close the door? We have this sort of similarity matrix, and we want some of those elements in this similarity matrix which will act as the positive pairs. Again, how we take positive pairs in this setup, we take an image and we apply the same stochastic transformation pipeline twice. We get two different augmentations. We show that the most important transformations are random cropping and then resizing for practical reasons. And also color jittering, so distorting the statistics of the mean values of the pixels so that the model is not able to have this information leak. So basically this shortcut learning from just matching the pairs by only matching the color histogram. So this is what we saw last week. So if you read the paper, this SimCLR paper, there is this objective function, and they say that they formulate it as a classification problem. Okay, so in the classification problem, at least in the supervised setting, I know that we have like a network and then a softmax over A and X, and then softmax over the dimension of the different classes. So here we have 6 classes, and the distribution looks something like this. Whatever. So this is before the softmax. And after we apply the softmax, what happens to these unnormalized logits? Like intuitively, why we apply softmax and not just convert them, just divide with their sum to make all these values from 0 to 1? What is the... So we're in the supervised learning setup. We have a paired data, X are the inputs, Y are the labels. And we have some probability distribution. Basically, we want to convert the logits, the output that is unnormalized, H here, to some probability distribution. Why do we apply softmax? Does anybody remember, maybe from deep learning? Yes?
Push the over the variables and like the ones that are bigger get bigger in comparison to this model.
Exactly. So this will have like a much higher probability. We intensify it, we increase the intensity. All right. So let's go back in the setup of contrastive learning. Since we have a classification problem, we have to see how many classes do we have. Does anybody know how many classes we have here for this example of 4x4 matrix? How many classes do we have to classify among? Yes? Almost. So basically, if you take the row, we exclude the diagonal elements. So if you take the row, the first row, so we have image 1, view 1, and the 3 different columns. This is a positive pair. Wait, I have to get this. This is a positive pair. And we have 2 negative pairs. So basically, the number of classes is 3. we maximize this similarity, and the denominator includes the negative pairs. The softmax basically where we apply, it's from 1 to 2 times n. N is the bad size. So the classification problem, if we use another letter here, m, is 2n minus 1. These are the classes of the classification, so like this classification problem. So the positive pair is just the similarity that we want to push together. So there's a connection between the logits here in a supervised setup. So basically the similarities in each row will act as the logits in a supervised classification problem. Any questions? Okay, it's a bit unintuitive to understand, but you can think that in each row we have similarities and they act as unnormalized logits where we want to make a classification problem. So basically the label here, if this is like, maybe I write it down, the cross entropy is okay, if we use just probabilities, it's P target log, let's use Y, Y target log Y predictions. So basically the target is here, because this loss only shows what happens for a positive pair ij, so the target is 1. So the probability would be, we push probability to 1 of the similarity, which acts as the logits, similarly, like analogously to having like a classification problem. Is this connection established to some extent? Alright, so we have 2 times the bad size minus 1 classes, and how many negatives? So since one class acts as the positive, we have number of negatives, 2 times n minus 2. Do we agree with that? One class should act as the positive where we want to push all the similarities. So there are some problems here. So this similarity between Zi and Zj, how do we implement that? Do you remember? In practice, what do we do? How do we measure similarity between 2 vectors? Yes? Sorry? Almost. What's the difference between the dot product and the cosine similarity? Yes. I, J. All right. So this similarity here, this sim notation, indicates that these 2 vectors, before we take their dot product, we need to normalize them in some way. So you probably all know that after L2 norm, as shown in the top right figure, this is an illustration on the 3-dimensional space. So it will result in a sphere, because all the vectors that live in this sphere have a unit, in a unit sphere, will have a norm of 1, right? So all the vectors that reside in this hypersphere need to have like a unit vector. Unit length, sorry. Do we agree that all the vectors after L2 normalization will have like a unit length? Okay. All right. I want to emphasize, to give you some intuition, why we apply L2 norm or any type of normalization in self-supervised learning, representation learning, pretext task. We will see this all the time, and it's not properly shown in the different literature, papers, publications, whatever. So the idea behind it lies in the softmax. So let's take again the supervised example. We have 6 classes, and in the beginning, the network will assign, a randomly initialized network will assign uniformly the predictions. So this would be like 1 divided by 6, 1 divided by 6. So like a completely randomly initialized network with no inductive bias would roughly assign these probabilities. Do we all agree? All right. So then, after a couple of iterations, or because of the inductive bias, for example, if you have convolutional neural networks on natural images, you have a slightly higher probability in the, let's say, in the desired class, but it's still very close to the other probabilities. So we want to intensify this difference. But here, we have similarities. Similarities are dot products. And what is the problem with dot products? So let's say we ignore this term, and we have 2 arbitrarily large dot products. So let's say we have d dimensions. In practice, we have 128 dimensions, but we could have 256, 512, 1024. There's nothing method-wise from the theory that limits us to use this 128 that we use in practice. So this kind of correlates roughly to another module, but the bottom line is that if we treat these d dimensions as independent, even if they have an expected value, a mean of 0, so we have 128 dimensions with 0 mean and unit variance, you can prove, I will not show this now, we showed this in the previous semester, that the dot product will still have a mean of 0, but its variance is really high. And if you assume that the variance of the independent variables is 1, then the variance of the dot product is d. What does this imply? It implies that this dot product can get arbitrarily subtle. So it already is more subtle than we expected it to be because we have similarities and we have dot products. So do you understand? We have pairs of dot products. So do you understand the difference why we don't apply any normalization or scaling down factor here, while when we have pairs we need this scaling down? Is it clear? Okay. For those who are interested, the most popular nowadays operation to do deep learning with transformers, we haven't touched upon this topic in this course. It has an exactly similar effect. So, do you remember how the transformer operation is implemented? Does somebody remember? We have queries, keys, and values. So it has exactly this division here, has exactly the same motivation as L2 normalization. So basically here we have a huge matrix of dot products, and each dot product is scaled down with the square root of d. So d here is d here. This is a small parenthesis. I just want to show that there is some connections between the different modules we see throughout the course. Alright, in the case of supervised learning, self-supervised learning, we have everything in the hypersphere. So the only way that we can push two vectors, okay, we are in the 128 dimensional space, but you can always think some intuitions in the 2-dimensional space or 3-dimensional space. So let's say that this is a unit circle, which is not, but it's very hard to draw. So since the vectors need to live in the unit circle, so they cannot move here, so this vector cannot reduce its unit length, we can only push them together if we bring them closer. So after a couple of steps, if these are the augmentations from two different images before training, after training there will be something like this. This will be view 1, view 2. Agree? Any questions so far? So the normalizations help us, basically the model, to ignore the magnitude and just focus on the dot product. The dot product corresponds to this, the cosine similarity of this angle. Okay. Then here I have a very nice illustration I found online about the temperature. So you divide by the temperature and you say why we use a temperature of 0.1 or 0.5. So if you check the paper, they say we play with values from 0.1 to 1 and we find that 0.1 works better for large batch sizes and 0.5 acts better for small batch sizes, something like that. So this division with the temperature, you can visualize it as a way to increase the average confidence that something, so here we don't have losses, we have similarities, but this is for a simple classification problem, and this red line indicates a high temperature. So as temperature goes lower and lower, so 0.1, this the logic gets much more sharper and much more confident. Okay, so now we know why we do the L2 normalization, we do the softmax, but what is exactly happening after training? So during the exercise we have this TSNE visualization. I don't know how many of you managed to produce this plot, but it doesn't look that great. So basically TSNE is just a small indication of how things would look like from the 128 dimensional space to 2-dimensional space. I don't trust these plots personally, but it's interesting to see if we could have some indication, some undeniable evidence that something is happening. So let's start from the experimental part. So this team from MIT analyzed a small convolutional neural network, I think some variation of AlexNet, trained with contrastive loss. And they provide some theoretical as well as empirical evidence that during this loss, the features are approximately asymptotically uniformly distributed in this hypersphere. And second, that views from the same image, what we call as positive pairs so far, tend to get much closer together. So this is the first plot is about the uniformity. So here you can imagine the different vectors indicating to these different tiny images. And here is the two features that are brought closer together, similarly to the 2-dimensional side. And they also argue that if you are able to nicely separate everything in the hypersphere, then you can come up with very good linear classifiers, what we do with linear probing in the exercise that we train another linear layer to classify the images afterwards. Okay, so they say that positive pairs should be mapped to nearby features. And below I'm writing invariant to unnecessary details. Any idea what do I mean by unnecessary details in practice? How do we inject what is necessary and unnecessary? You implemented it last week. Yes?
Data augmentation?
Exactly. So basically, independent of the two different distortions here, these two vectors need to map together. Alright? So this is why they write about unnecessary details. As we will see, this objective is more general than RGB images. So first, they provide some empirical evidence. So on top left, we have a histogram of distances, so mean square error distances. So basically mean square error, if everything is L2 normalized, is very similar to cosine similarity. I will show that, but it's not important at the moment. So on top left, we have a supervised model, so a model that is trained with human annotated data to classify different classes like images, dogs, whatever, and we take the feature space of this learning model. And here we have the exact same architecture, but trained with contrastive learning. So here, with the dust vertical lines, we see the mean L2 distance, and this is much smaller than the supervised model. What does that may indicate? That empirically we can see that if we distribute everything in the unisphere, that the positive pairs would be even closer than training the model with a supervised objective. Is that clear? And then they do some low dimensional projections, and they also see some sort of uniformity, which is this circle is much more consistent than the top one, which is from supervised learning. Any questions? All right. Okay, we have some experiments. We can quantify this. We can experimentally identify this, but can we come up with some quantified results? Because so far what I present is more qualitative. Right. And the answer is yes, at least for the contrastive laws with these small networks. So they define, so they take a bunch of positive pairs, so augmentations from the same image, and they take the expectation, like just the average, over this mean square error, and they define this alignment score. And the uniformity score is again the same mean square error distance, just passed from this log sum x operation. Why they do this? This took me some time to figure out. I started to have some initial intuition. So the idea is that here we have positive pairs, and here we have random data that are probably negative pairs. So it's not, basically this term assigns different portions of the metric, of this uniformity metric, for small and large distances, because we raise everything to this x to the minus t power. Okay, let's say 4.
This is 0.
So basically, we pay more attention, we put so much more effort to the pairs that lie close together than the ones that are far away. So let's say this 4 is t times and they set this t hyperparameter to 2. So basically, and what does this tell us? Like if we consider that this could be the cosine similarity, since the cosine similarity lies from -1 to 1, the maximum cosine similarity that between two vectors is 2. So we want to ignore pairs of images, for example, an image with a cat versus an image with an airplane will be in this area here, so kind of down-weighted, while an image of a cat and a dog with the exact same background, like blue sky, green grass, would be somewhere here. Because we care about creating, to push away cats and dogs with the same background, for example. This is like some small intuition why they derive, why they apply this radial-based function. So in machine learning theory, there is this idea of kernel method, this radial-based function, which is nothing more than taking the exponent with this hyperparameter t. So they define this kernel. Okay, let's ignore t. So this is a really commonly used kernel function in standard machine learning algorithms like support vector machines. We'll not go too much into it. I just want to make some small connection with probability distributions, because this is totally empirical. This has nothing to do with probability theory. But insofar, we can show some connection with the isotropic Gaussian distribution. We will just not pay attention to this. This is just a constant. I'm writing it just for completeness. So the connection between this hyperparameter here and this hyperparameter is probably obvious. Agree? So we can roughly say that the distance between two randomly sampled pairs, kind of probably negative, is conceptually to having a Gaussian distribution, basically the distance or the density assigned from x with their distance to the mean. But these two parts are just some proportional approximation. It's not some strict mathematical definition. They are definitely not equal. That's why I say that everything is like an approximation. We don't actually have a uniform distribution or anything. So the mean here would be x prime. So basically I want to establish this connection between probabilities. In the paper they argue that it's like nicely tied this metric with normal distribution. Any questions so far? Okay. Which brings us to the next part. So if you managed to work with the exercise, you probably saw, and also Felix talked about the connection between the lower bounds of mutual information and how this is connected to the bat size. So can somebody explain the connection with the mutual information and bat size? Does somebody remember what we discussed in the last lecture with Felix? No? Yes?
There was some expected value which had a high variance, thus multiplier approximation is better with high edge size and reverse low edge size.
Yes, and what happened in the extreme case where we have an infinitely large bat size? We had like a kind of a very good approximation of mutual information, right? So this is what I want to establish. So in practice, we trained with 512 or 1000, but to squeeze the last bits of performance, you need a large bat size. Why do we need a large bat size? Because there is a connection between the bat size and the number of negatives. So from each mini bat, we extract the negatives. So they are kind of coupled. I had this somewhere here. So for n bat size, we had 2n minus 2 negative samples. So the problem is not the bat size itself, it's its connection to the number of negatives. So we need a lot of negative samples. How about if we decouple those two values? We need to come up with a new notion of negatives. And for that, they borrowed some idea that was published in 2018. This is not the paper we're going to emphasize. It's just that it's using a memory bank. What is a memory bank? It's basically a data structure. Or so this is the, let's use the letter K. So this is the 128 vectors, so the embedded dimension. And these are some initially, in the beginning we randomly initialized these values, drawn like sample from a normal distribution, but as we move into different steps of training, we're going to update these vectors. So K here is the length of the cube, and it's much bigger than bat size. We intentionally define the length of the cube to be much larger than the bat size. In practice, we also need to make like a multiple of the bud size, but this is not really important. So you can imagine for a bud size of 256, the paper we will discuss about, which has the abbreviation called MoCO, uses 65,000. So it's the hyperparameter here is 65K, and this is 256. So we use basically a huge number of negatives, even though the bud size stays 256. So how we do that? We have a pointer, and at each iteration we update those vectors. So let's say if this is k and bud size is 2, in the first iteration we will update those two values, and then we move the pointer here. But every time we use the whole Q as negatives. Then in the second iteration, this is the first iteration. So here I'm illustrating for bud size of 2 and K, the number of rows here. So in the second iteration we update these values, we move the pointer here, and so on. So this is how we keep, basically we use the negatives from the previous iterations. We start with random initialization, and as we move on, we create a dynamic queue or dictionary that is updated at every step with the previous mini batches. And in the end, we throw away when we update these values. We throw the oldest one. So after the pointer moves here, it comes back again in the beginning. Any questions about the queue? So they formulate the contrastive loss as a dictionary lookup problem or query-like lookup problem. There is a lot of inspiration from all these methods from information retrieval. So they take this info-NC, what we say as the contrastive loss. They add the memory bank, which is much larger than the mini bud size. I use the letter B. And then they found a problem. What is the problem? We will use the word key for the output of the basically it's bud size times B, and here we have the Q. Oh. No, this is not correct. So basically the Q is updated in the initial experiment. The Q was updated with the values passed from the encoder, and this didn't provide stable results. So they came up with this idea of the momentum encoder. So since they keep basically, since they update their dictionary while they use the output of the encoder, even if we say that here this is the encoder and here you just do tensor.detach, this didn't work in practice. So they came up with this thing, they call it momentum encoder. We will use it extensively in representation learning, but it's also used in other fields like reinforcement learning. As we call it exponential moving average over the parameters. So the exponential moving average over the parameters, I prefer the notation of student-teacher, so I will use this notation. So the teacher model is an exponential moving average over the encoder or the student will be updated only with a small ratio at each step. So m is a value from so we only update, so m in practice is something 99%. So at each time we only pass 1%, 1% of the student parameters to the teacher. And this is the only way they could make this approach work. And then they argue that this makes the teacher much more consistent, because we progressively update the dictionary from all the previous iterations. So also the values that we update need to be like a moving average of the past iteration, and this makes this way they create this consistent memory bank. So I try to provide some indication why they not just use a memory bank and detach the gradients and update the dictionary, but they also use an exponential moving average over the parameters of the encoder. That's what they mean by momentum encoder. We will also use the word teacher in the course. Any questions? Okay. Yeah, here I explain, they write in the paper that they hypothesize that it's attributed to the rapidly changing encoder, and this may indicate, because it's still a hypothesis, that it reduces the representation's consistency. So I want to emphasize on the consistency part here. And EMA stands for exponential moving average, usually over the parameters when we talk about models. So the objective that was initially, this is the info and C or contrastive loss, becomes this thing here, this expression, where the keys, these are the exponential moving average of the current minibat, and this is the whole Q. Well, I don't like this notation here. You can just replace this term with Q capital. So if we were to rewrite this, we would write LQ equals minus log the transpose. Okay, we have it. Okay. We use the capital letter T for the transpose and the small letter t for the temperature. I'm rewriting this with a capital L because I don't want you to confuse this K here with this K here. So this is the output of the current minibat, and this is the whole memory bank. And also in the implementation, this is a matrix multiplication, while this is a Bat's matrix multiplication. It happens everything for each imaging pen. So I just want to re-emphasize that K is built as a dynamic Q, and it's consistent. This is pseudocode. I will also give you a notebook where you can study a very simplistic implementation without I've removed everything related to distributed data parallel. I will just give you a notebook because the initial idea was to ask you to implement it as an exercise, but then we thought it's too much. So we'll just give you, if you want to study, because some students said that they have a big gap between discussing about this model in the lecture and implementing themselves. So I will just provide you with a pseudocode with this function, how it will work in actual code, but not a complete solution with trained models and fine-tuning. And in practice, we use a Q length of 65,000, the momentum is something like 9%, and they have a deep temperature. And one small issue that is caused many times, it's batch normalization. So even if you have a great idea, you may still miss it because of some unintentional information leakage or shortcuts that may happen. And over the last few years, so batch normalization was invented between 2015 and 2016, and then ResNets came out and everybody used this normalization method. But as time goes by, it looks like we start to using it less and less. And this is one more indication that it causes problems. So the problem is that the model can exploit local information leakage, as it's called. So basically it's kind of cheating. But you only have this problem, so this local, you only have this problem when you do distributed training. So you have multiple GPUs and each GPU sees only, so you have a mini batch, so of 256, and you can distribute this in as many GPUs as you want and do the computations in parallel and then compute the gradients and then take the average gradient. So this is something that is completely unrelated to what we've talked so far. It's like an engineering thing. But for large data sets like ImageNet with 1 million images, you can't really avoid the engineering part of distributed training. And it looks like the model could cheat from the local batches of its GPU. It could exploit the local information. So there are different ways to encounter this problem. So SimCLR use this, as it's called in the literature, synchronized batch normalization. So you have an intermediate step when you aggregate the statistics, so the average over the means and the standard deviations. So